Okay everybody, in this video we're going to talk about what is probably going to be your best friend in trig, and that is the unit circle. I consider this equivalent to knowing your times tables. We know multiplication is repeated addition, but when you're in a college algebra class, I don't think we should be doing, 7 times 6 by going, okay, 7 plus 7 plus 7, so on. We want to have these things down quicker so that we're not falling behind in our work. Same for the unit circle. I think it is crucially important that we know where these values come from. I can't overstate that enough, that we need to know where these or how these cosine and sine values are generated. But once you have that understanding, I don't want to see you in a calculus class having to figure out sine of 5 pi over 3 and having to draw a special right triangle every time. It's time consuming. At some point we need to treat this like our multiplication tables, and we just need to be able to expedite the process a bit. So in this video I want to go through how do we generate these things and how can we use the unit circle to help us down the road. So first thing that I'm going to probably say many times over is you really just need to focus on quadrant 1. If you know all the cosine and sine values for quadrant 1, you're set. Now this video is going to assume or go off the idea that you have some prior knowledge of some trig topics. So I'm expecting that we already kind of know our radian and degree measurements around the unit circle, and that you have some understanding of the special right triangles like a 30-60-90 triangle and a 45-45-90 triangle. We'll review those, and I want to show you how we're going to use them. So first of all, what I'm going to do is I'm going to fill in the degree measurements for all these angles around the triangle around the circle, followed by the radian measurements. So I guess I'll put those down here. So this would be 0 degrees or 360 if you were to go, all the way one lap around. So often you'll see 0 and 360 written. But here's our common angles, 30, 45, 60, and this would be 90. And again, the reason we are interested in those common angles, the 30, 45, and 60, is because those correspond to our special right triangles. Those are right triangles that have a special relationship between the three side lengths that is guaranteed to be true if you are sitting in that type of a triangle, a 30, 60, 90, or a 45, 45, 90. We'll do that in a sec. Every other angle on this circle is some combo of these slices, okay? So what I talk about or how I would go about finding them is to basically utilize the reference angle. So if I'm looking at this angle up here, oops, I missed it, this angle right here, and I want to know what is that angle. What I really ask myself is, how did I slice my pizza? Did I cut my pizza into small slices? Or did I cut my pizza into the medium-sized slices? Or did I go for it and did I cut my pizza up into the big 60-degree slices? Okay, well, when determining what kind of slice you have, look at half your pizza and see how close you are to closing off the half. So when I'm looking at the half of the pizza, I'm looking at this angle as what's left. This is one big slice needed to close off half my pizza. And that really right there, again, what we've talked about is that is my reference angle. That is how far I am off the horizontal x-axis. Again, wherever your angle terminates, however far you must go, the quickest way to get to the x-axis, whether it's up or down, that is your reference angle. That's telling you the type of slice you have used to cut up your pizza. So this reference angle is 60 degrees. I know that if I were to go all the way around half the circle, half my pizza would be 180 degrees. So if I want to figure out what this angle is in blue, it's simply 180 degrees all the way down, and then give back the 60 degrees that I overshot by, making this angle 120 degrees. Okay, I hope you've got some familiarity with that already. Okay, this would be 120 degrees. Doing the same thing but with the 45-degree size slices, you would find that this triangle over here, or this angle over here, is 135 and 150. And what some people do is dangerous. They look at these three and they go, oh look, it bumps up 15 degrees every time. 15, 15. I think that is a dangerous way to memorize these angles. Think about how you cut the pizza. how you cut the pie, what size slices are you dealing with? Little guys, the medium-sized guys, or the big slices? That is your reference angle, and that is going to take you much, much further than looking at little patterns here. So similarly, say I just want this angle down here. Okay, I want to know, what is that angle? Again, I need to know, well, how did I choose to cut up the pizza in this case? Did I use little slices, medium slices, or big slices? So to answer that, you find your reference angle, which again is the fastest way you can get to the x-axis, to half your pizza. The fastest way I can get there is straight up to it. And so I'm saying, oh, okay, well, I've cut this down into little slices. The little slices being 30 degrees. That's my reference angle. So again, I'm going to count to my nearest anchor point, my x-axis. There's 180 degrees, and it's got to be 30 more to get to that terminating side. So this angle down here would be 210 degrees. And I could do that again for the 45-degree slice, and again for the 60-degree slice. Again, if I want this angle, I got to say, well, how did I cut the pizza? The closest way to get to the x-axis is straight up to it, and that says, well, look, I used the big slices. So my reference angle is 60 degrees. So if I go to 180 and 60 more, that puts me at 240. Oh, I just realized I did the math wrong here. This is not 235. This should be 225. Don't skip steps. Go too fast. That's how mistakes happen. Anyways, let me just fill in the rest of these for us. Let's see, 330. And let me put in the radian measurements as well. That's what the other line is for. And again, hopefully you've got some prior knowledge about radian measurements. So the radian measurements for these guys are going to be pi over 6, pi over 4, pi over 3, pi over 2. Radians are awesome because they tell you the reference angle right off the bat. Over here at 120, this is 2 pi over 3s. And so you can spot the reference angle right away. Oh, you cut this into pi over 3 size slices, and you're telling me you have 2 of them. 1 of them, 2 of them. 2 of those big 60-degree size slices. So radians truly are way more friendly to use. They just take some getting used to initially. So again, I'm going to jump through all this, assuming that you've already kind of discussed radians, have some idea of how I'm generating these. If not, that's something you want to get familiar with real quick. So let's see, this would be 5 pi over 4s. This would be 4 pi over 3s. Just to share quickly how I'm doing this, again, I'm always working with my anchor point. So say I'm looking for this guy, the 4 pi over 3, and I want to know, well, how did I figure out that that's 4 pi over 3? What I'm not doing is I'm not converting the degrees down into that. That's too time consuming. Again, I'm thinking about my reference angle. How did I cut my pizza? So again, for looking at half the pizza, I can say, all right, well here I've got a big slice. The shortest way to close off the x-axis is with a big slice. A pi over 3 size slice is my reference angle. Once I know that that's how I've cut the pizza, I've cut them into pi over 3 size slices, I look at my anchor point there, and I say, all right, well, how many would fit here, halfway? To get down to pi, that would be 3 pi over 3s, wouldn't it? Because the 3's would cancel and to give you just pi. So I know here to here, halfway around the pizza is 3 pi over 3s. So if I go 1 more pi over 3, that's how I get down to 4 of them. Okay. So again, I'm doing this part real quick, going off the assumption that you've had some practice with this already. So let me see, this would be 11 pi over 6. Let's see, these are pi over 4s, that would be 7 of them. Pi over 6s, this would be, pi over 3s, this would be 5 pi over 3s. And I'm going to write this as 0 or 360, because if I go all the way around, now I'm at 360, or 0 or 2 pi. Okay. All right. Well, that's the first key. you've got to feel good about getting those angles down. Okay, don't bother going on until that feels secure. The next key is to get the cosine and sine values. Now, every ordered pair here is going to be in the format cosine first and then the sine value for that angle. All right, let's pick on one of these triangles to begin with. Let's pick on the small slice of pizza, the 30-degree or the pi/6 size slice. And let's do all of those slices in the unit circle here. So this is where we need to remember our special triangles. In a 30, 60, 90 triangle, we know the following is going to happen. The side opposite the 30 is typically referred to as A, but whatever it is, the side opposite the 60 is guaranteed to be radical 3 times that side. Okay, so if this A right here, if that's really a 5, then this is guaranteed to be 5 radical 3. That will always happen in a 30, 60, 90 triangle. The hypotenuse, guaranteed to be twice A. All right? That's why we are interested in memorizing this angle and not, 20 degrees. You don't see 20 degrees on your unit circle and memorize the cosine and sine, because a 20, 70, 90 triangle would not have a nice unique relationship like this. All right, so I'm going to calculate the sine and cosine values by thinking of good old Sohcahtoa. Remember, this tells you which trig function you've got, and it tells you which side lengths to divide depending on what angle you're standing at. So let's work on this 30-degree triangle. Again, the x value, the first data point here, is going to be my cosine value. So let's stand at 30. That's my standing point. What's cosine of 30? All right, or pi/6 if you're working in radians. Well, Ka says it would be the side adjacent divided by the side opposite of my angle. So adjacent to my 30-degree angle is this, divided by the hypotenuse of that triangle. I think that's what I said back there. Doesn't matter what a's are because they're going to cancel. You're always going to get down to cosine of 30 is always going to be rad 3/2. Let's see if I could fit that in here. Okay, let's find sine now. How about sine of 30? All right, so again, consulting Sohcahtoa. So says for sine, take the side opposite your angle and divide it by the hypotenuse. So standing at 30, the side that's opposite my angle is side A, and dividing it by the hypotenuse, 2A. Again, it doesn't matter what A was because it's going to go away, and I'm going to be left with just 1/2. Sine of 30 is always 1/2. Okay. Well, here's the beautiful thing about reference angles. Sine and cosine of 30 are consistent, but they're also going to be exactly the same for every single angle on the wheel that has a that is coterminal to 30, or rather, I'm sorry, not coterminal, that has a reference angle of 30. Okay, so envision this. Take this slice of pizza and flip it over onto this side. Wouldn't that give me this slice over here? I just flipped it over. Okay, kind of treat this like a mirror image and flipped it over that. In doing so, it didn't shrink, it didn't expand, it didn't grow. So in other words, the ratio of the side lengths is the same. In other words, this radical 3 and this 1/2, this data point here is the same as this data point here, almost, right? If I want to get to that data point on the right, I had to go right radical 3 and up 1/2 to get there. All I'm going to need to do here is I'm going to need to go left radical 3/2 and up 1/2 to get there. Okay, so again, I hope you're getting this idea that the length or these side lengths didn't change. It's just the direction that I have to go to get to that terminal point changed. So I'm going to go left a distance of rad 3/2, making it negative rad 3/2. And I'm going to go up a distance of 1/2, just like I did for the other one. And there are my cosine and sine values for 150 degrees, or for 5 pi/6. I didn't have to do this again. And that's what I mean about what I said earlier, where you want to know quadrant 1, and if you know all the cosine and sine values for quadrant 1, you know them for the entire circle. You're set. Okay? Let's finish off all these 30-degree reference angles. So where's the next slice on here that's a 30-degree slice? That's a slice this size. I see one down here. So what you can imagine here is, it's maybe hard to visualize, but envision that what's going on is, how about this yellow triangle here was flipped over the y-axis, giving me this kind of a shape, and then that was flipped, I can't really draw it, but flipped upside down over the x-axis, giving you this triangle. So we get this triangle here by simply flip-flopping this original yellow one. Flip it over the y-axis, flip it down over the x-axis. If you're just flipping it, it's not growing, it's not shrinking. Again, the side lengths aren't changing at all. So in order for me to get to this terminal point, again, I had to go right radical 3 over 2 and up 1/2. Well, then to get down to this terminal point, it's the same distance, it's just different directions. I need to go left radical 3 over 2 and down 1/2. All right, so let me clean up this picture, or get rid of some of this stuff. So in doing so, if I go left radical 3 over 2 and down 1/2 to get here, my data point would be negative rad 3 over 2 and negative 1/2. And boom, there is the cosine and sine value for 210, or 7 pi over 6. So once I knew this one cosine and sine value for a 30-degree reference angle, I had it locked in for this 30-degree triangle, and this angle that has a 30-degree reference angle, and this angle that has a 30-degree reference angle. Last would just be this angle that has a 30-degree reference angle. All right, so envision this last one. Again, to get to this terminal point here, I had to go right radical 3, up 1/2. Do you see that I'm just taking this blue triangle and I'm flipping it over the x-axis, and it lands kind of upside down. Again, it didn't shrink, it didn't grow. So to get to this terminal point, right, and again, I'm only doing the angles that have a reference angle of 30 degrees. I'm only worried about that size slice of pizza at the moment. To get here, I am going to go right radical 3 over 2, but now I need to go down 1/2. So again, let me try and clean this up. Here, to get here, I got to go right radical 3 over 2, and then down 1/2. So it's negative. And there are my cosine and sine values for that particular angle. Now, I remember learning unit circle, and what I had to do is I had to draw it from scratch many, many times, and not just copying it and memorizing it, but doing exactly what I'm doing here, sort of justifying to myself how I create these. And I can't recommend enough that that's how you do it. The beauty is this is going to go really quick for you. I want to point something out to you down here. Here's something to remember. All students take calculus. All students take calculus. What this tells me is this is a clever way to remember that of your 4 quadrants, it tells you which trig function is positive there. So in quadrant 1, all trig functions are positive. In quadrant 2, only sine is positive, and therefore so is cosecant, because it's just the reciprocal. In quadrant 3, tangent is positive, and in quadrant 4, cosine is positive. And I could see that in the work I did up here. Come back up here. Let's remember all students take calculus. In quadrant 1, cosine and sine were positive. In quadrant 2, look, it says sine should be positive. That means everyone else is negative. Well, yep, the sine was positive. Remember, sine is the y value here. And everybody else, the cosine was negative. In quadrant 3, tangent would be positive. You may or may not know yet, but tangent, you could take the sine value divided by the cosine value. A negative divided by a negative would be positive. And then in quadrant 4, where cosine should be negative, we see that's exactly what happened. I'm sorry, where cosine should be positive, we see that's exactly what happened, and sine was negative. So again, all students take calculus helps us to remember in which quadrant each trig function will be positive or negative. That allows us to only know the first quadrant's worth of sine and cosine values. Okay? Because, take a look at this. Suppose they ask me to find, I don't know, sine of, well, let's just do 11 pi over 6. I'll go with that. Actually, let's do it. Let me see here. Yeah, sure. For now, let's just do 11 pi over 6. First thing I would need to do, or the way I do it, is what's my reference angle? And again, the beauty with radians is, boom, there's my reference angle. I cut the pi into pi over 6 size slices, and I have 11 of them. Okay, so automatically, sine of any pi over 6 reference angle is a half. I know that. It's half. The question in my mind is, should it be positive half or negative a half? And that depends on the quadrant we live in. So then all I do is I think, okay, well, where is this angle? 11 pi over 6, I know that that's going to be down here. All students take calculus means that in quadrant 4, where this angle terminates, the cosine should be positive, but everyone else should be negative. That means my sine should be negative. Sine of 11 pi over 6 equals negative 1/2. And it may be funky at first, but I promise you this is going to really accelerate your ability to find these trig function values. This is absolutely how it's happening, and you should definitely know this process, but it's not how you should do every single problem. Every time you're asked to find sine of an angle or cosine of an angle, this can get time consuming. So you do want to know that how to build the wheel, but once you are able to build it, I would then use your work, use quadrant 1, use all students take calculus to go ahead and expedite or fast track this stuff. Let's do the 45-degree angle real quick. So now that we've got all the 30-degree reference angles done, let's look at the 45-degree size slice of pi. Let's pretend that that's how I chopped up my my pizza here. So there's a 45-degree slice I'll have to work on. There's a 45-degree slice. There's a 45-degree slice. Let's get this first one squared away. Okay. Well, one of my other special triangles is the 45, 45, 90. And in that right triangle, because the two angles here are both 45, it's isosceles. Whatever the side length is here, just say we call it A, this side length opposite 45 is the same, and it's guaranteed that the hypotenuse will be radical 2 times whatever A was. So if this is 10, then this is also 10, and this is going to be 10 rad 2. Guaranteed, because it's a 45, 45, 90. That doesn't happen with, say, a 40, 50, 90 triangle, and that's why we don't bother to memorize sine of 40. Okay. Well, now that we've got this, let's use Sohcahtoa to figure out our cosine and sine. If I want cosine of 45, I got two of them. Let's just pretend this is the one I'm standing at. Cosine is ka, adjacent to 45 over the hypotenuse. So adjacent to 45 is that over the hypotenuse. I get A over A radical 2. Again, the A's are always going to cancel. That's why it doesn't matter what they are. I get 1 over radical 2, which is correct. Typically, we rationalize this, multiply top and bottom by rad 2, and you would see it written that way. Cosine is rad 2 over 2. Let's do sine. Sine of 45 degrees, again, sine is take the side opposite your angle, divide it by the hypotenuse. So opposite of my chosen angle is again an A. Hypotenuse is still A rad 2. A's cancel. And if I rationalize, I'm there again. Cosine and sine are the same at a 45-degree angle. All right? So let's plug those into my unit circle here. For 45 degrees, the cosine, remember cosine first, cosine is rad 2 over 2, and sine is also rad 2 over 2. Okay? All right, so now what about all these other 45-degree angles? So what about this guy? Any other angle whose reference angle is 45. And again, remember your reference angle is what's the fastest way to get to half your pizza, up or down. So if I'm looking at this angle, this 135-degree angle right there, that's what I'm interested in. Say I want cosine of 135. Again, do you notice what's happening? Isn't this blue angle just flipping over the y-axis to give me this green triangle here? All right. And so this ordered pair, in order to get to this terminal point here, I had to go right 2 radical 2. Wait a minute. I had to go right radical 2 over 2 and up radical 2 over 2. To get to this terminal point, I just need to go left radical 2 over 2 and up. So since I'm going left, I would have negative rad 2 over 2, rad 2 over 2. That's it. So that's one way I could generate the rest of these, just like I did with the 60-degree angles. I could just think of this triangle flipping over axes. And so, in other words, these are I'm going to have the same cosine and sine values for every single angle whose reference angle is 45, or pi over 4. The only thing that's going to change is whether it's a plus or minus, depending on the quadrant. So let's get them even faster now. Now that we know all students take calculus, let's get this guy. If I want this angle, okay, well, I can identify that it's a 45-degree size slice. The quickest way to the x-axis is a 45-degree angle. All right, that's my reference angle. I know that every single cosine of 45-degree reference angle will be rad 2 over 2. And sine of any angle whose reference angle is also rad 2 over 2. I'm sorry, sine of any angle whose reference angle is 45 is also rad 2 over 2. So this would be rad 2 over 2 and rad 2 over 2, but let's remember this. All students take calculus. So if I am down here in this quadrant, my terminating side is in quadrant 3. In quadrant 3, only tangent should be positive. Everyone else should be negative. So this would be a negative and a negative. Negative cosine, negative sine. Let's do the last one. I got a 40, let's say my last 45-degree reference angle would be right here. Right? 45-degree size slice to close off that pizza. So my reference angle is 45. Since my reference angle is 45, I know for a fact the cosine is rad 2 over 2 and the sine is rad 2 over 2. What I need to verify is the sine. All students take calculus. In quadrant 4, where that angle terminates, cosine should be positive. So the x value, the cosine value, should be positive, but that means the other guy, the y, should be negative. Which makes sense. If I'm trying to get to this terminal point, I have to go right, therefore positive x, and down, therefore negative y. All right, I hope you're starting to see how we can kind of speed this up. Let's do the last one here. Let's do the 60-degree angle. Now, if I'm standing on a 60-degree angle, it's the same. I'm still using my 30, 60, 90 special triangle. It's just that now I'm standing at 60 degrees. That's where I'm standing. So if I want cosine of 60 degrees, cosine again is adjacent over hypotenuse. So the side that's adjacent to 60, it's tight in the picture here, but that's A, and the hypotenuse is 2A. I get a half. And sine of 60 degrees, sine is opposite over hypotenuse, so the side opposite 60, oopsies, is this guy, A radical 3 over my hypotenuse. All right, so for my 60-degree angle, cosine is guaranteed to be a half, sine is guaranteed to be rad 3 over 2. All right? And those ratios are going to be repeated throughout the entire circle. Anywhere you've got an angle whose reference angle is 60, you're looking at the cosine and sine values. aside from maybe a plus or minus sign. So let's look at this guy. At 120 degrees, remember that's a 60-degree reference angle. That's the size slice of pizza I'm dealing with. It's always how far are you, or what's the closest way to get to the x-axis. Since it's 60 degrees, I'm guaranteed that cosine is a half, sine is rad 3 over 2. You could think about the plus or minus sign two ways. To get to this terminal point, I had to go left and up. Since I went left, my x value should be negative, and I went up, so the y value should be positive. Or, all students take calculus tells me that the sign should be positive. It is. And everyone else should be negative. It is. So it's just another way to think about it. Let us get this angle that has a 60-degree reference angle. Again, because the closest distance to the x-axis is that. That's the fastest way to close off or get to the x-axis is straight up at it, and that's the big slice. That's a 60-degree size slice. Since it's a 60-degree reference angle, I know what cosine and sine are. It's a half and rad 3 over 2. Guaranteed. What I need to make sure I do before I move on is get the signs correct. You could think of this as I went left and down. That tells me that they would both need to be negative to get to that ordered pair. Or the fact that all students take calculus, and in quadrant 3, the only one that should be positive is tangent, and everyone else should be negative. Let's do the last one. This guy, 300 degrees or 5 pi over 3, 60-degree reference angle, meaning I know cosine and sine. It's guaranteed to be 1/2 and rad 3 over 2. Let's get our signs squared away. I went right and down. Oops, a little far. I went right and down. So right means positive x, down means negative y. Or you could remember that all students take calculus, and so that's showing me that in this quadrant cosine should be positive, and it is. Okay. So I hope you're getting this idea. Oh, and for these quadrantal angles, this is a unit circle, so therefore it means it has a radius of 1. So I could just fill these data points in here. This data point would be 1, 0, 0, 1, negative 1, 0, 0, negative 1. And so what you're looking at you are looking at the cosine and sine values of 0 degrees, or 360. And you're looking at the cosine and sine values for 90 degrees, or pi over 2. Cosine and sine values. Okay, I don't think you can absorb this in one sitting. And again, I remember learning this, and I remember creating this wheel over and over and over and over again until I just had it down. And it truly, for me, was one of the best things I did because it unlocked Trig for me. You're going to be doing so many problems down the road that are going to be interesting and fascinating and challenging, and you don't want this to be the challenging part of it. This is going to be one tiny piece of the whole problem you're doing. You don't want that to be the part that you're getting held up on. You don't have time for that. So invest some time in the unit circle. Make sure you know how it's created. Fundamentally, make sure you know how it's created, because if you understand that, you're not going to have to sit here and memorize or come up with gimmicks or tricks on how to memorize this unit circle. You will understand it, it'll stick with you, and it'll be a really useful tool in your arsenal. All right. Good luck with it.